Geometrical isomerism in hydrocarbons. The type of isomerism in which organic compounds have similar molecular and structural formula, but differ in the arrangement of their functional groups or atoms is called geometrical isomerism or cis-trans isomerism. For example, cis-1,2-dichloroethene and trans-1,2-dichloroethene are geometric isomers. They have same molecular formula, C2H2Cl2, and the same structural formula. But in cis-1,2-dichloroethene, both chlorine atoms are on the same side of the double bond, while in trans-1,2-dichloroethene, chlorine atoms are on opposite sides of the double bond. Two necessary conditions have to be satisfied for the existence of geometrical isomerism in hydrocarbons. Compound must possess carbon-carbon double bond, and each carbon atom must have two different groups or atoms attached to it. Let us study the concept of geometrical isomerism in saturated hydrocarbons, like alkanes, and the unsaturated hydrocarbons, like alkenes and alkynes. Geometrical isomerism in alkanes. During formation of a saturated hydrocarbon, like 1,2-dichloroethane, each carbon atom shares one electron with the other, forming carbon-carbon single bond. Thus, one of the two necessary conditions of having a carbon-carbon double bond is not satisfied here. As you can see, carbon atoms in this compound can rotate around each other, during which the degree of overlap between atomic orbitals remains unchanged. This rotation around the bond results in a different configuration of the molecule, but these are not isomers, as one configuration can be obtained from the other just by rotating or twisting around the carbon-carbon single bond without actually breaking or making any bonds. Hence, in 1,2-dichloroethane, geometrical isomerism is not possible. Geometrical isomerism in alkenes. In unsaturated hydrocarbons, like 1,2-dichloroethene, carbon-carbon double bond consists of a sigma and a pi bond. Sigma bond is formed by sharing one electron each between the two carbon atoms. The pi bond is formed by sideways overlapping of two parallel p orbitals of two carbon atoms, above and below the plane of carbon atoms. If two carbons attempt to rotate around each other, p orbitals will no longer be in parallel position, but the bond will not rotate at room temperature. Hence, two chlorine atoms get locked on opposite sides of the double bond. This is called the trans isomer. To get different configuration of the molecule, chlorine atoms will have to be arranged themselves in a different way, in which they get locked on the same side of the double bond. This is called the cis isomer. Here, both the necessary conditions, that is, the presence of carbon-carbon double bond, as well as the presence of two different groups attached to carbon, are satisfied. Hence, geometrical isomerism is possible in alkenes. However, at higher temperature, when the isomers obtain sufficient amount of energy, that is 251 kilojoules per mole, pi bond is broken. Thus, isomerism is not possible at higher temperatures. Geometrical isomerism in alkynes. In unsaturated hydrocarbon, like 1,2-dichloroethane, each carbon atom shares 3 electrons to form carbon-carbon triple bond. Out of these, one is a sigma bond, while the remaining 2 are pi bonds. At the same time, only one chlorine atom is attached to each of the carbon atoms, and geometry of the molecule is linear. Here, none of the necessary conditions for a geometrical isomerism are satisfied. Thus, geometrical isomerism is not possible in unsaturated hydrocarbons like alkynes. Summary: we have seen that in saturated hydrocarbons like alkanes and unsaturated hydrocarbons like alkynes, geometrical isomerism is not possible, whereas in unsaturated hydrocarbons like alkenes, geometrical isomerism occurs due to the restricted rotation of carbon-carbon double bond.